You are standing on a planet that was once completely frozen from pole to equator. A lifeless ball of ice drifting through space, where temperatures never rose above freezing anywhere on the surface. For tens of millions of years, Earth was entombed in ice a kilometer thick, the oceans sealed beneath frozen shells, the continents buried under glaciers. No open water, no rain, no sound but the crack of shifting ice. And yet, somehow, life survived. Here's something even stranger. Right now, beneath your feet, there's an ocean. Not water, but molten iron spinning at thousands of degrees, generating an invisible force field that wraps around the entire planet. Without it, Earth would look like Mars, a dead, airless rock, stripped bare by solar wind. The ground you're standing on? It's moving, drifting. The continents have wandered thousands of miles, and they're still moving, millimeters each year, pulled by currents of liquid stone beneath the crust. And the air you're breathing? It was once the deadliest poison on Earth, released by ancient bacteria that triggered the planet's first mass extinction. The oxygen that keeps you alive killed almost everything that came before. Every atom in your body was forged in the heart of a dying star billions of years ago. You are, quite literally, made of stardust. Walking on a world that shouldn't exist, breathing air that was once toxic, protected by forces you cannot see. Tonight, we're going to drift through 100 quiet truths about our home. Not the Earth you think you know, but the Earth that actually exists. A planet that has frozen solid and thawed, that has been struck by objects the size of Mars, that has lost most of its atmosphere and rebuilt it, that has seen life nearly vanish and somehow return. Some of what you hear may surprise you, some may disturb you, but all of it is real. Hello there, and welcome to Sleepable Science. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts and planetary mysteries, rather than counting sheep. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if gravity itself has softened. Because tonight, we're exploring the only home we've ever known, Earth. Not the simplified version from textbooks, but the real, dynamic, impossibly complex world that has shaped every moment of life's 4 billion year journey. If these calm, curious explorations help you unwind or give you a quiet way to end your day, consider subscribing to Sleepable Science. It helps others find their way here too. One sleepy soul at a time. Now, let's begin. Birth and fire and dust. Earth is 4.54 billion years old, give or take 50 million years. We know this not from guesswork, but from radiometric dating of ancient rocks and meteorites, using the decay of radioactive isotopes like uranium-238 to lead-206. The oldest rocks found on Earth's surface in northwestern Canada are about 4.03 billion years old. But Earth itself is older. The solar system formed from a vast cloud of gas and dust called the solar nebula, remnants of previous generations of stars that had lived and died, enriching space with heavy elements. About 4.6 billion years ago, this cloud began to collapse, probably triggered by the shock wave from a nearby supernova explosion. As the cloud collapsed, most of the material fell toward the center, forming the sun. But some remained in a spinning disk around the young star. Within this protoplanetary disk, dust grains collided and stuck together through static electricity and gentle gravitational attraction. These grains grew into pebbles, pebbles into boulders, boulders into planetesimals, small bodies a few kilometers across. Over millions of years, these planetesimals collided and merged, building up into larger and larger objects. Some became the planets. Others were scattered or destroyed in violent impacts. The inner solar system, where Earth formed, was hot, Light elements like hydrogen and helium were blown away by the solar wind, leaving behind rocky, metal-rich bodies. Earth grew through this process of accretion, sweeping up material in its orbital path. As it grew, its gravity increased, allowing it to capture larger and larger objects. Heat from these impacts, combined with heat from the decay of radioactive elements, melted the growing planet. In this molten state, Earth underwent differentiation. Heavy elements, primarily iron and nickel, sank toward the center, forming the core. Lighter silicate minerals floated upward, forming the mantle and eventually the crust. This process was remarkably efficient. Within tens of millions of years, Earth had a distinct layered structure that persists today. But Earth's formation was not smooth or gentle. The early solar system was a chaotic place, filled with debris and rogue planetesimals. And one of these objects would change Earth forever. About 4.5 billion years ago, shortly after Earth had mostly formed, a Mars-sized body called Theia collided with our planet. The impact was cataclysmic, one of the most violent events in Earth's history. Computer simulations based on the Moon's composition and orbital characteristics suggest Theia struck at an oblique angle, perhaps 45 degrees. The collision vaporized both Theia's crust and much of Earth's outer layers. Rock turned to gas. Gas turned to plasma. For a brief moment, Earth may have had a rock vapor atmosphere. The cores of the two bodies merged, adding Theia's iron to Earth's growing core. But the lighter material, the crustal and mantle rock, was blasted into orbit. This debris ring, made of vaporized and molten rock, eventually coalesced to form the Moon. This giant impact explains several mysteries. It explains why the Moon is so large relative to Earth, the largest moon-to-planet ratio of any rocky planet in the solar system. It explains why the Moon's composition is similar to Earth's mantle, but lacks a large iron core. The impact stripped away lighter materials, leaving the dense core of Theia buried deep within Earth. And it explains why Earth's day is 24 hours long. The collision gave our planet its spin, its rotation, its rhythm. After the Moon formed, Earth was still a hellish place. The surface was covered in oceans of magma, glowing molten rock that slowly radiated heat into space. The atmosphere, if it existed at all, was a thin veil of vaporized rock and gases belched from volcanic eruptions. The young Moon, much closer than it is today, loomed enormous in the sky, pulling tremendous tides not through water, but through molten stone. Slowly, over millions of years, the surface began to cool. Solid crust formed, broke apart as fresh magma welled up from below, then reformed. Volcanoes erupted constantly, releasing water vapor, carbon dioxide, nitrogen, and other gases that would eventually become our atmosphere. Rain fell for the first time, evaporating before it reached the ground. But as the planet cooled further, the rain began to pool. The first oceans formed, shallow, acidic, and hot, but liquid. By 4.3 billion years ago, there was liquid water on Earth's surface. We know this from chemical signatures in ancient zircon crystals found in Western Australia, which suggests they formed in the presence of water. This is remarkable because it means Earth had oceans earlier than many scientists once believed, less than 200 million years after the planet itself formed. But Earth was not yet finished being bombarded. Between about 4.1 and 3.8 billion years ago, the inner solar system experienced a period called the Late Heavy Bombardment. Evidence from lunar samples and crater counts on the Moon suggests that asteroids and comets, their orbits disturbed by the migration of the giant planets Jupiter and Saturn, rained down on Earth, the Moon, and the other inner planets. On Earth, these impacts would have created enormous craters, some hundreds of kilometers wide. They would have melted the crust, vaporized water, and possibly evaporated parts of the early oceans. The largest impacts may have sterilized the surface, boiling away any early attempts at life. The moon still bears the scars of this bombardment. Its craters, preserved in airless silence, tell the story of violence that Earth experienced but has since erased through geological activity. Every dark patch you see on the moon, the Maria or seas, were formed when massive impacts fractured the lunar crust and allowed lava to flood the surface, creating the smooth basaltic plains we see today. Yet somehow, in the midst of this chaos, in a world still being pummeled by space rocks, in oceans that alternated between boiling and freezing, life began. The first breath of life. Life on Earth began at least 3.8 billion years ago, possibly even earlier. We don't know exactly when or exactly how, but we know it happened relatively quickly after the planet became habitable. This rapid emergence suggests that life, or at least the chemistry that leads to life, may be a natural consequence when the right conditions exist. The earliest evidence comes from carbon isotopes in ancient rocks from Isua, Greenland. These rocks, 3.8 billion years old, contain ratios of carbon-12 to carbon-13 that hint at biological activity. Living organisms preferentially use the lighter carbon-12 isotope during metabolism, leaving behind a characteristic chemical signature that can persist for billions of years. While this evidence is debated, some scientists argue the signature could result from non-biological processes. It remains one of our oldest potential traces of life. More dramatic evidence comes from stromatolites, layered structures built by colonies of cyanobacteria and other microbes. Fossilized stromatolites have been found in rocks 3.5 billion years old in the Pilbara region of Western Australia. Living stromatolites still exist today in places like Shark Bay, Western Australia, where conditions, high salinity, low nutrients, remain similar to those of the ancient Earth, limiting the animals that would otherwise graze on the microbial mats. These early microbes lived in a world utterly alien to us. The atmosphere contained almost no free oxygen. Instead, it was composed primarily of nitrogen, with significant amounts of carbon dioxide, methane, and trace amounts of ammonia and hydrogen sulfide. The sky would have been orange or perhaps brown, not the blue we know today, which requires oxygen molecules to scatter sunlight. The oceans were murky, filled with dissolved iron that would later rust and precipitate when oxygen appeared. For nearly 2 billion years, almost half of Earth's entire history, our planet was a microbial world. Life existed, but only as single cells or simple colonies. No plants, no animals, no fungi. Just bacteria and archaea, living in the oceans, clustering around hydrothermal vents, colonizing hot springs, and perhaps forming thin films in shallow coastal environments. Then, about 2.4 billion years ago, everything changed. And the change came from the smallest, most unassuming organisms imaginable. Cyanobacteria, photosynthetic microbes that had been quietly living in the oceans, began producing oxygen as a waste product of photosynthesis. They had evolved a remarkable biochemical pathway, one that could split water molecules, use the hydrogen to make organic compounds, and release the oxygen. At first, this oxygen didn't accumulate in the atmosphere. It was immediately consumed by chemical reactions with dissolved iron and other reduced minerals in the ocean. Vast deposits of banded iron formations, rocks with distinctive red and black layers, formed during this time as oxygen combined with ferrous iron to create ferric iron oxides, which precipitated to the sea floor. These banded iron formations exist on every continent and represent one of the largest chemical transformations in Earth's history. Trillions upon trillions of tons of iron being oxidized and dropping out of solution. The ocean, which had been greenish-black or murky from dissolved iron, slowly cleared as the iron was removed. But eventually, after hundreds of millions of years, the oceans became saturated with oxygen. All the available iron had been oxidized. The rocks on land had absorbed what they could, oxygen began to escape into the atmosphere. This event, called the Great Oxidation Event or the oxygen catastrophe, transformed Earth forever. And here's the twist that should make you pause. For countless anaerobic organisms, organisms that thrived in an oxygen-free world and had dominated Earth for over 1 billion years, oxygen was a deadly poison. It damaged their cellular machinery, destroyed their metabolic pathways, and killed them outright. The first mass extinction in Earth's history wasn't caused by asteroids or volcanoes or ice. It was caused by photosynthesis, by life itself. Organisms that had ruled Earth for eons were wiped out, not by some external catastrophe, but by the metabolic waste product of their neighbors. It's one of the greatest ironies in the history of life. The gas that now sustains complex life was once Earth's most potent toxin. Yet from this catastrophe came extraordinary opportunity. Oxygen is a powerful electron acceptor, which means it can be used to extract far more energy from organic molecules than anaerobic metabolism allows. Organisms that could harness oxygen through aerobic respiration could extract up to 18 times more energy from the same food than their anaerobic ancestors. This extra energy fueled the evolution of larger, more complex cells. It made possible the development of eukaryotes, cells with nuclei and complex internal structures. It paved the way, eventually, for multicellular life, for animals, for consciousness, for us. Today, Earth's atmosphere is about 21% oxygen by volume. Every breath we take is a gift from ancient cyanobacteria, from photosynthetic algae, from the countless plants that blanket the continents. The oxygen that sustains us was once Earth's deadliest poison, transformed over billions of years into the foundation of complex life. The rise of oxygen also created the ozone layer. Ozone, a molecule made of 3 oxygen atoms, forms in the stratosphere when ultraviolet light from the sun splits oxygen molecules apart and they recombine into O3. This ozone layer shields the surface from harmful UV radiation, radiation that damages DNA and makes unprotected life on land nearly impossible. Before the ozone layer, life was confined to the oceans, protected by water that absorbs UV light. The ozone layer, a direct consequence of oxygen-producing photosynthesis, opened up an entirely new realm for life to explore: the land. But the transition to an oxygenated atmosphere wasn't smooth or instant. Oxygen levels fluctuated wildly for hundreds of millions of years. There's evidence of periods when oxygen levels dropped again, possibly due to changes in volcanic activity or the burial of organic matter. The path from a reducing atmosphere to an oxidizing one was neither simple nor predictable. What's clear is that life and atmosphere evolved together, each shaping the other in a complex dance that continues today. Earth's atmosphere is not a static backdrop for life. It is a product of life, maintained and regulated by the biosphere in ways we're still working to fully understand. The layers we live between Earth's atmosphere extends hundreds of kilometers above the surface, but most of its mass is concentrated in the lowest layer. If you could compress the entire atmosphere to sea level pressure and temperature, it would form a layer only about 8 kilometers thick, roughly the height of Mount Everest. The atmosphere is divided into 5 main layers, each with distinct characteristics determined by how temperature changes with altitude. The troposphere is the lowest layer, extending from the surface to about 8 to 15 kilometers high, depending on latitude. Lower at the poles, higher at the equator. This is where we live, where clouds form, and where nearly all weather occurs. Temperature decreases with altitude in the troposphere, dropping about 6.5 degrees Celsius per kilometer. At the top of the troposphere is the tropopause, a boundary where temperature stops decreasing. Above the troposphere lies the stratosphere, extending from the tropopause to about 50 kilometers altitude. Here, temperature increases with height, a reversal caused by the presence of ozone, which absorbs ultraviolet radiation from the sun and converts it to heat. This temperature inversion makes the stratosphere very stable. There's little vertical mixing, which is why commercial aircraft often fly in the lower stratosphere to avoid turbulence. The ozone layer itself peaks around 20 to 25 kilometers altitude. Despite its importance, the ozone layer is remarkably thin. If you could compress all the ozone in a column of atmosphere into a layer at sea level pressure and temperature, it would be only about 3 millimeters thick. Above the stratosphere is the mesosphere, extending from 50 to 85 kilometers. Temperature again decreases with altitude here, making it the coldest part of Earth's atmosphere. The mesosphere is where most meteors burn up, creating the shooting stars we see at night. It's also where rare, high-altitude clouds called noctilucent clouds form, made of ice crystals at temperatures as low as 120 degrees Celsius. The thermosphere extends from the mesosphere to about 600 kilometers. Despite its name, the thermosphere experiences enormous temperature variations. In the hot thermosphere, temperatures can exceed 1,500 degrees Celsius. Though the air is so thin that you wouldn't feel hot if you were there, the thermosphere is where the International Space Station orbits, and where auroras occur when charged particles from the sun interact with atmospheric gases. Finally, the exosphere is the outermost layer, extending from about 600 kilometers to 10,000 kilometers, where it gradually fades into the vacuum of space. Here, atmospheric particles are so far apart they rarely collide with each other. Some can even escape Earth's gravity entirely. The atmosphere's composition has remained relatively stable for the past several hundred million years. About 78% nitrogen, 21% oxygen, 0.9% argon, and 0.04% carbon dioxide, with trace amounts of other gases. But this stability is recent on geological timescales, and it's maintained by active processes. Nitrogen, the most abundant gas, is relatively inert. It cycles slowly through the biosphere, converted to ammonia by nitrogen-fixing bacteria, taken up by plants, returned to the atmosphere by decomposition and denitrifying bacteria. This nitrogen cycle is essential for life, as nitrogen is a key component of proteins and DNA. Carbon dioxide, though present in tiny amounts, has an outsized influence on climate through the greenhouse effect. CO2 molecules absorb and re-emit infrared radiation, trapping heat that would otherwise escape to space. Without any greenhouse gases, Earth's average temperature would be about 18 degrees Celsius instead of the current plus 15 degrees Celsius. The difference between a frozen planet and a habitable one. Water vapor is Earth's most important greenhouse gas, accounting for about 60% of the greenhouse effect. But water vapor content varies enormously, from nearly zero in cold, dry regions to 4% in hot, humid tropical areas. Water vapor also forms clouds, which both reflect sunlight, cooling effect, and trap heat, warming effect, making their net climate impact complex and dependent on altitude and type. The atmosphere also protects us from space hazards. Most meteors, even those several meters across, burn up in the mesosphere due to friction with air molecules. Only the largest survive to hit the surface. The atmosphere also shields us from high-energy cosmic rays and solar radiation, though this protection is enhanced by Earth's magnetic field. Atmospheric pressure decreases exponentially with altitude. At sea level, the weight of all the air above presses down with a force of about 101,325 pascals, or roughly 1 kilogram per square centimeter. At the summit of Mount Everest, pressure is only about 1/3 of sea level. At the altitude where jets cruise, it's even lower, which is why cabins must be pressurized. This pressure gradient drives wind and weather. Differences in temperature create differences in pressure, and air flows from high pressure to low pressure, redistributing energy around the globe. The rotation of Earth deflects these winds through the Coriolis effect, creating the prevailing wind patterns. Trade winds. Near the equator, westerlies in mid-latitudes, polar easterlies near the poles. Weather itself, the day-to-day variations in temperature, precipitation, wind, and cloud cover, emerges from the complex interplay of these processes. Energy from the sun heats the surface unevenly, creating convection currents. Water evaporates and condenses, absorbing and releasing enormous amounts of latent heat. The atmosphere, ocean, and land surface interact, exchanging energy and moisture. Climate, in contrast to weather, is the long-term average of these conditions. Earth's climate has changed dramatically over geological time, from hothouse periods when no permanent ice existed anywhere to icehouse periods when ice sheets extended far beyond the poles. Understanding these past climate changes helps us understand what controls Earth's temperature and what the future might hold. The ocean planet water is Earth's defining feature. About 71% of the surface is covered by ocean, with an average depth of about 3,688 meters. The total volume of ocean water is roughly 1.335 billion cubic kilometers. Where did all this water come from? This question has puzzled scientists for decades, and the answer is still being refined. Some water was almost certainly present in the rocky material that accreted to form Earth, trapped in minerals as hydroxyl groups or in pockets as ice in asteroids and planetesimals. As Earth heated during its formation and differentiation, this water would have been released through volcanic outgassing, gradually building up an ocean and atmosphere. But did Earth's original water survive the giant impact that formed the moon? Computer models suggest much of the water present before the impact would have been lost, vaporized, or blown off into space by the collision. This has led some scientists to propose that much of Earth's water arrived later, delivered by comets and water-rich asteroids during the late heavy bombardment. Recent measurements complicate this picture. The ratio of deuterium, heavy hydrogen, to normal hydrogen in Earth's ocean water doesn't match well with most comets measured so far. Comets tend to have much higher deuterium ratios, but it does match certain types of asteroids, particularly carbonaceous chondrites, which contain significant water bound in minerals. The current scientific thinking, based on isotopic evidence and computer modeling, is that Earth's water likely came from multiple sources, some from the original building blocks of the planet, some delivered by asteroids during the late heavy bombardment, and perhaps a smaller contribution from comets. However it arrived, water has been present on Earth's surface for most of the planet's history, at least 4.3 billion years based on zircon evidence, possibly earlier. And its presence changed everything. Liquid water is essential for life as we know it. It's an excellent solvent, dissolving and transporting minerals and nutrients. It can exist in all three phases: solid, liquid, and gas, at temperatures and pressures common on Earth's surface. It has unusual properties like high surface tension and the fact that ice floats, which prevents oceans from freezing solid from the bottom up. The ocean is not uniform. It's layered, with distinct zones based on depth, temperature, and salinity. The surface mixed layer, the top 100-200 meters, is stirred by wind and waves, keeping temperature and salinity relatively uniform. Below this is the thermocline, where temperature drops rapidly with depth. Deeper still is the deep ocean, cold, 2 to 4 degrees Celsius, dark, and under immense pressure. Ocean water circulates on two scales. Surface currents, driven primarily by wind, create great circular patterns called gyres in each ocean basin. The Gulf Stream, for instance, carries warm water from the Gulf of Mexico along the eastern coast of North America and across to Europe, moderating climate on both sides of the Atlantic. But there's also a deeper circulation, driven by differences in temperature and salinity. This thermohaline circulation, sometimes called the global conveyor belt, operates on a timescale of about 1,000 years. Here's how it works. In the North Atlantic, near Greenland and Iceland, surface water cools and evaporates, becoming both colder and saltier. This makes it denser than the water below, so it sinks, forming North Atlantic deep water. This deep water flows southward along the ocean floor, eventually reaching the Southern Ocean around Antarctica, where it joins the Antarctic Circumpolar Current. From there, deep water flows northward into the Indian and Pacific Oceans, gradually warming and rising as it mixes with surface waters. Eventually, it returns to the surface, flows back toward the Atlantic as a surface current, and the cycle begins again. This conveyor belt redistributes enormous amounts of heat. The Gulf Stream and its extension, the North Atlantic Drift, carry roughly 1.4 petawatts of heat northward, equivalent to about 100 times the world's energy consumption. This is why Western Europe is so much warmer than corresponding latitudes in North America or Asia. But the conveyor belt is not constant. Paleoclimate records show it has slowed or even shut down during past climate changes, with dramatic effects on regional temperature and precipitation patterns. The addition of large amounts of fresh water from melting ice sheets can disrupt the sinking of dense water in the North Atlantic, potentially weakening or stopping the circulation. The ocean also plays a crucial role in Earth's carbon cycle. Seawater absorbs CO2 from the atmosphere, where it can dissolve to form carbonic acid or be taken up by photosynthetic plankton. When these organisms die, some of their carbon sinks to the deep ocean, effectively removing it from the atmosphere for hundreds to thousands of years until deep water upwells again. Over longer timescales, carbon in the ocean precipitates as calcium carbonate, forming the shells and skeletons of marine organisms. When these organisms die, their shells settle to the seafloor, eventually forming limestone and other carbonate rocks. This process, operating over millions of years, has locked away enormous quantities of carbon that would otherwise be in the atmosphere as CO2. The ocean is also home to an astonishing diversity of life, from microscopic phytoplankton that form the base of the marine food web to the largest animals ever to exist, blue whales, which can reach lengths of 30 meters and weights of 200 metric tons. Different zones of the ocean support different communities. The sunlit surface waters, or photic zone, extending to about 200 meters depth, are where photosynthesis occurs. Here you find phytoplankton, the small fish and zooplankton that eat them, and the larger fish and mammals that eat those. Below the photic zone lies the aphotic zone, where no sunlight penetrates. Life here depends on organic matter sinking from above, or, in special cases, on chemical energy from hydrothermal vents. These deep-sea environments remained almost completely unknown until the mid-20th century. The deepest parts of the ocean, the Hadal zone below 6,000 meters, are found in ocean trenches formed at subduction zones where one tectonic plate slides beneath another. The Mariana Trench in the western Pacific reaches a maximum depth of about 10,994 meters at the Challenger Deep. At this depth, pressure exceeds 1,000 times atmospheric pressure at sea level, enough to crush most submarines. Yet even here, life exists. Specially adapted fish, shrimp, and microbes thrive in the cold, dark, high-pressure environment. Expeditions have found amphipods, snailfish, and other creatures that would be crushed if brought rapidly to the surface. The ocean remains one of the least explored parts of our planet. We have better maps of the surfaces of Mars and the Moon than we do of the ocean floor. New species are discovered regularly, and entire ecosystems, like the hydrothermal vent communities discovered in 1977, remain to be explored. The engine beneath. Beneath your feet, the Earth is not solid. The crust, the rocky shell we live on, is only 5 to 70 kilometers thick, depending on whether you're standing on ocean floor or continental landmass. Beneath that lies the mantle, a layer of hot, dense rock extending down to about 2,900 kilometers. The mantle is solid, but it behaves like a very slow liquid over geological time. Heat from the core below warms the lower mantle, making it less dense. This warmer rock rises slowly, while cooler, denser rock near the surface sinks. This process, called mantle convection, churns the interior of Earth like a pot of thick soup simmering on a stove. Except the pot is thousands of kilometers deep and the simmering takes millions of years. This motion is the engine that drives plate tectonics, volcanic activity, and mountain building. It's the reason continents drift, oceans open and close, and mountain ranges rise where plates collide. At the center of Earth lies the core, a sphere of iron and nickel about 7,000 kilometers in diameter, roughly the size of Mars. The core is divided into two parts. The outer core, extending from 2,900 to 5,150 kilometers depth, is liquid metal. The temperature here is estimated at 4,000 to 5,000 degrees Celsius, hot enough to keep iron molten despite the immense pressure. The inner core, from 5,150 kilometers to the center at 6,271 kilometers, is solid despite temperatures exceeding 5,000 degrees Celsius. It remains solid because of the extreme pressure, about 3.6 million times atmospheric pressure at sea level, which raises the melting point of iron above the actual temperature. The core formed during Earth's early differentiation, when heavy elements sank toward the center. The heat in the core comes from three sources: residual heat from Earth's formation, when countless violent impacts converted kinetic energy to heat, heat from the decay of radioactive elements like uranium, thorium, and potassium, and heat generated by the gradual solidification of the inner core as the planet slowly cools. As the inner core crystallizes, it releases latent heat and lighter elements, which rise into the outer core. This, combined with Earth's rotation, drives convection currents in the molten outer core. These currents, combined with Earth's rotation, generate a magnetic field through a process called the geodynamo. Earth's magnetic field is invisible, but it's one of the planet's most important features. It extends thousands of kilometers into space, forming a protective bubble called the magnetosphere that deflects the solar wind, a stream of charged particles constantly flowing from the sun, preventing it from stripping away Earth's atmosphere. And here's why that matters. We know what happens when a planet loses its magnetic field. Mars once had a magnetic field, generated by convection in its core. Measurements from orbiting spacecraft have detected remnant magnetism in ancient Martian crust, particularly in the southern highlands, indicating that a global magnetic field existed early in Mars's history. But as the smaller planet cooled faster than Earth, its core solidified and the magnetic field disappeared, likely sometime between 4.1 and 3.9 billion years ago. Without that protection, the solar wind slowly stripped away Mars's atmosphere over hundreds of millions of years. Energetic particles from the sun literally knocked atoms out of the Martian atmosphere and into space. The planet that may have once been warm and wet, with rivers and perhaps oceans, transformed into the cold, dry desert we see today. That could have been Earth. Our magnetic field has protected our atmosphere for over 4 billion years, allowing water to remain liquid, allowing life to emerge and evolve. Without it, Earth's story and ours would have been very different. But Earth's magnetic field is not constant. The geological record preserved in volcanic rocks shows that the field has reversed many times throughout Earth's history, the north and south magnetic poles switching places. These reversals occur irregularly, averaging about once every 300,000 to 400,000 years, though intervals vary widely from tens of thousands to tens of millions of years. The last reversal occurred about 780,000 years ago, meaning we're arguably overdue for another one based on the average. During a reversal, which can take several thousand years to complete, the magnetic field weakens significantly. Some scientists have worried this might leave Earth vulnerable to increased solar radiation But evidence from past reversals doesn't show corresponding mass extinctions or dramatic environmental changes. Some animals can sense Earth's magnetic field and use it for navigation. Birds like robins and European robins use magnetic sense during migration, traveling thousands of kilometers with remarkable precision. Sea turtles use geomagnetic signatures to return to the beaches where they hatched, sometimes traveling across entire ocean basins. Even some bacteria contain chains of magnetite crystals that align with the magnetic field, helping them orient themselves to find optimal oxygen levels in sediments. The magnetic field is not just protection, it's part of what makes Earth habitable, a living world rather than a barren rock. It's a reminder that our planet is alive in ways we often don't see. Beneath the stillness of stone, there is motion, heat, and energy. A slow fire that has burned for billions of years and will burn for billions more. The wandering continents. If you could watch Earth from space in time-lapse over millions of years, you would see something astonishing. The continents would drift across the surface like ice flows on a slow-moving river, colliding, merging, breaking apart, and drifting away again. In 1912, a German meteorologist and geophysicist named Alfred Wegener proposed a radical idea. He suggested that the continents had once been joined together in a single supercontinent, which he called Pangaea, meaning all Earth in Greek. According to Wegener, Pangaea broke apart about 200 million years ago, and the continents slowly drifted to their current positions. Wegener's evidence was compelling. The coastlines of South America and Africa fit together like puzzle pieces, particularly if you match the edges of the continental shelves rather than the current shorelines. Identical fossils of plants and animals, including the reptile Mesosaurus and the plant Glossopteris, were found on continents now separated by vast oceans. These organisms couldn't have crossed thousands of kilometers of open water, suggesting the continents were once connected. Mountain ranges on different continents had matching rock types, ages, and structural features, as if they were once part of a continuous chain later split apart. Geological formations in Scotland matched those in eastern North America. The Appalachian Mountains aligned with mountains in Scotland and Scandinavia. But Wegener couldn't explain how continents could move. He suggested they plowed through the ocean floor like ships through ice, driven by tidal forces from the moon and centrifugal force from Earth's rotation. Most geologists rejected this idea as physically impossible. How could solid rock push through other solid rock? What force could be strong enough to move entire continents? The scientific community didn't just disagree with Wegener. They ridiculed him, mocked him. At conferences and in journals, his ideas were called utter damned rot, delirious ravings, and moving crust disease. His peers dismissed him as a meteorologist who didn't understand geology, an outsider who had wandered into the wrong field. Wegener died in 1930 during an expedition to Greenland to study ice cores and weather patterns. He was 50 years old. He died believing most of the scientific world thought he was wrong, that his life's work had been rejected. But here's what makes his story both tragic and triumphant. He was right. It wasn't until the 1960s, more than 30 years after his death, that new discoveries vindicated his ideas and led to the development of plate tectonics. The breakthrough came from an unexpected place, the ocean floor. In the 1950s and 60s, oceanographers mapping the seafloor with sonar discovered vast underwater mountain ranges called mid-ocean ridges running through all the major ocean basins. The Mid-Atlantic Ridge, for instance, runs down the center of the Atlantic Ocean, from Iceland to the Southern Ocean. But these ridges weren't just mountains. They were active volcanic zones where new oceanic crust was being created. Magma welled up from the mantle, cooled, and formed new seafloor, which spread outward from the ridge in both directions. This process, called seafloor spreading, explained how continents could move, They were being pushed apart by the creation of new ocean floor between them. More evidence came from magnetic surveys. As new oceanic crust forms at mid-ocean ridges, magnetic minerals in the cooling lava align with Earth's magnetic field. When the field reverses, the next batch of lava records the reversed polarity. The result is a pattern of magnetic stripes on the seafloor, symmetric on both sides of the ridge, recording the history of magnetic reversals. This pattern proved seafloor spreading was real and allowed scientists to calculate the rate of spreading, typically a few centimeters per year. But if new ocean floor is being created at ridges, where does it go? It can't accumulate forever, or Earth would be expanding. The answer was found at ocean trenches, where oceanic crust bends downward and slides beneath continental crust, or another oceanic plate in a process called subduction. The oceanic crust returns to the mantle, where it melts and is recycled, completing the cycle. By the late 1960s, these discoveries were synthesized into the theory of plate tectonics, which revolutionized geology. The lithosphere, the rigid outer shell of Earth, including the crust and uppermost mantle, is broken into about a dozen large plates and several smaller ones. These plates move independently, driven by mantle convection currents, ridge push, and slab pull as subducting crust sinks into the mantle. Where plates interact, geology happens. Divergent boundaries, where plates move apart, create mid-ocean ridges, and on land, rift valleys like the East African Rift. Convergent boundaries, where plates collide, create different features depending on what collides. When two oceanic plates converge, one subducts beneath the other, creating deep ocean trenches and volcanic island arcs like Japan. When an oceanic plate meets a continental plate, the denser oceanic crust subducts, creating volcanic mountain ranges like the Andes. When two continental plates collide, neither can subduct easily, so the crust crumples and thickens, building massive mountain ranges like the Himalayas. Transform boundaries, where plates slide past each other horizontally, create faults like the San Andreas Fault in California, where the Pacific Plate moves northwestward relative to the North American Plate. The continents have indeed wandered, just as Wegener proposed. About 335 million years ago, the continents began merging to form Pangaea. By 200 million years ago, Pangaea was at its maximum extent, a single landmass stretching from pole to pole. Then it began to break apart. First, Pangaea split into two pieces: Laurasia in the north, North America, Europe, and Asia, and Gondwana in the south, South America, Africa, Antarctica, Australia, and India. Later, these supercontinents fragmented further into the continents we know today. The Atlantic Ocean didn't exist 200 million years ago. It formed as Pangaea broke apart and continues to widen today at about 2.5 centimeters per year, roughly the rate your fingernails grow. But Pangaea wasn't Earth's first supercontinent, and it won't be the last. Evidence from older rocks reveals a pattern. Supercontinents assemble and break apart in a cycle lasting about 400,600 million years, called the supercontinent cycle. Before Pangaea, there was Rodinia, which formed about 1.1 billion years ago and began breaking apart around 750 million years ago. Before that was Nuna, also called Columbia, which assembled about 1.8 billion years ago. And before that, the record becomes unclear, but there are hints of even older supercontinents stretching back into the Archean eon. Why do supercontinents break apart? The prevailing theory involves mantle dynamics. When a supercontinent forms, it acts like a thermal blanket, trapping heat beneath it. Eventually, this heat builds up enough to create mantle plumes, hot upwellings that reach the surface, causing the continent to dome upward and eventually rift apart. As the continent fragments, new ocean basins open, and the cycle begins again. The continents are still moving today. GPS measurements confirm that Africa and South America are separating at about 2.5 centimeters a year. India continues pushing into Asia at about 4 to 5 centimeters a year, which is why the Himalayas are still rising. The Pacific Plate slides northwestward past North America at about 5 centimeters a year. The East African Rift is slowly pulling apart, and in tens of millions of years, it may become a new ocean, splitting Africa into 2 continents. In the distant future, plate tectonics models suggest the continents may reassemble into a new supercontinent. Some models predict Pangea Ultima, where the Americas collide with Africa and Europe as the Atlantic closes. Others predict Amasia, where the Americas and Asia merge around the North Pole as the Arctic Ocean and Caribbean close. But this won't happen for hundreds of millions of years. For now, the continents continue their slow dance, driven by heat from Earth's interior, writing the story of our planet in the rocks and fossils they carry. Breathing Earth breathes, not with lungs, but through cycles that move elements between atmosphere, ocean, land, and life. These biogeochemical cycles, carbon, nitrogen, oxygen, water, sustain the biosphere and regulate climate. The carbon cycle is perhaps the most important for understanding climate. Carbon moves through Earth's systems on multiple timescales. On short timescales, days to years, plants absorb CO2 from the atmosphere during photosynthesis, using carbon to build tissues. Animals eat plants, using some carbon for energy and releasing CO2 through respiration. Decomposers break down dead organisms, returning carbon to the atmosphere and soil. The ocean absorbs CO2 from the atmosphere and releases it back, with the balance depending on temperature, biology, and ocean circulation. On medium timescales, decades to thousands of years, carbon moves into and out of soils, dissolved organic matter in the ocean, and living biomass. Forests can store significant carbon for centuries. The deep ocean can hold carbon for millennia before upwelling returns it to the surface. On long timescales, millions of years, carbon is locked in rocks. The weathering of silicate rocks consumes CO2, forming carbonate ions that wash into the ocean. Marine organisms use these ions to build shells and skeletons of calcium carbonate. When these organisms die, their remains settle to the seafloor, eventually forming limestone. Subduction carries some of this carbonate rock back into the mantle, where it melts and releases CO2 through volcanic eruptions, completing the rock cycle. This slow, carbonate-silicate cycle acts as Earth's thermostat. If CO2 levels rise, temperatures increase, which accelerates weathering through increased rainfall and chemical reaction rates, removing more CO2 and cooling the planet. If CO2 levels drop, cooling slows weathering, allowing volcanic CO2 to accumulate, warming the planet. This negative feedback has helped keep Earth's temperature within habitable bounds for billions of years. But this thermostat operates on million-year timescales. It can't respond to rapid changes like the current increase in atmospheric CO2 from burning fossil fuels. Fossil fuels, coal, oil, and natural gas are ancient organic carbon, formed from the remains of plants and microorganisms that lived hundreds of millions of years ago. This carbon was removed from the atmosphere over millions of years and stored underground. When we burn fossil fuels, we release this stored carbon in just a few centuries, far faster than natural processes can remove it. The nitrogen cycle is equally essential. Nitrogen is a key component of proteins, DNA, and other biological molecules. But atmospheric nitrogen gas, N2, is chemically inert and unusable by most organisms. Certain bacteria and archaea can fix atmospheric nitrogen, converting it to ammonia, NH3, or ammonium, NH4+, which plants can absorb. Some nitrogen-fixing bacteria live freely in soil. Others form symbiotic relationships with plants, particularly legumes, providing nitrogen in exchange for sugars. Animals obtain nitrogen by eating plants or other animals. When organisms die and decompose, nitrogen is released as ammonia. Other bacteria convert ammonia to nitrite, NO2, and then nitrate, NO3, in a process called nitrification. Plants can absorb nitrate as a nutrient. Other bacteria perform denitrification, converting nitrate back to nitrogen gas, completing the cycle. Humans have dramatically altered the nitrogen cycle through the invention of the Haber-Bosch process, which converts atmospheric nitrogen to ammonia for use in fertilizers. We now fix more nitrogen industrially than all natural processes combined, leading to nutrient pollution, algal blooms, and dead zones in coastal waters. The water cycle, or hydrological cycle, moves water through the Earth system. The sun's energy evaporates water from oceans, lakes, and soil. Water vapor rises, cools, and condenses into clouds. Precipitation returns water to the surface, where it may run off into rivers and back to the ocean, soak into the ground to become groundwater, or be absorbed by plants. Plants transpire water vapor through their leaves, returning it to the atmosphere. In tropical rainforests, transpiration is so intense that a significant fraction of rainfall is recycled. Moisture that evaporates from the forest generates clouds that rain back onto the forest. This creates a self-sustaining cycle that can break down if too much forest is cleared. About 97% of Earth's water is in the oceans, salty and largely unavailable for drinking or agriculture. Only about 2.5% is fresh water, and most of that is locked up in ice sheets and glaciers. Rivers, lakes, and accessible groundwater account for less than 1% of Earth's total water. The oxygen cycle is intertwined with carbon. Photosynthesis produces oxygen. Respiration and combustion consume it. Over short timescales, these processes roughly balance. But over geological time, the burial of organic carbon, in sediments and, over millions of years as fossil fuels, removes carbon without removing the corresponding oxygen, allowing oxygen to accumulate in the atmosphere. This is why atmospheric oxygen levels have remained relatively stable at around 21% for tens of millions of years, even though individual oxygen molecules cycle through the atmosphere, biosphere, and lithosphere on much shorter timescales. All these cycles interact. Changes in one affect the others. For instance, nitrogen pollution can stimulate algal growth in the ocean, which affects the carbon cycle by increasing photosynthesis. Deforestation reduces transpiration, affecting local rainfall patterns and the water cycle. Burning fossil fuels adds CO2 to the atmosphere and consumes oxygen, though the oxygen decrease is imperceptible given its abundance. Earth's biogeochemical cycles have kept the planet habitable for billions of years, but they can't respond instantaneously to rapid changes. Understanding these cycles is crucial for predicting how Earth's systems will respond to continued human alteration of the atmosphere, land, and ocean. Ice and fire. Earth's climate has swung between extremes throughout its history. From hothouse periods, when palm trees grew near the poles, to icehouse periods, when glaciers reached nearly to the equator, the planet has experienced conditions far outside what humans have known. Ice ages, periods when permanent ice sheets exist on at least one pole, have occurred several times in Earth's history. We're currently in an ice age that began about 2.6 million years ago, though we're in a warm period within it called an interglacial. But ice ages aren't uniform. They consist of alternating glacial periods, when ice sheets advance and cover large areas of continents, and interglacial periods like our current Holocene, when ice retreats to the poles. Over the past million years, these cycles have occurred with remarkable regularity, roughly every 100,000 years. What drives these cycles? The answer lies in subtle changes in Earth's orbit and axial tilt, known as Milankovitch cycles after Serbian scientist Milutin Milankovic, who calculated them in the early 20th century. Earth's orbit around the Sun is not a perfect circle, but an ellipse, and the shape of that ellipse changes over about 100,000 years, varying from nearly circular to more elongated and back. This affects how close Earth gets to the Sun, and thus how much solar radiation reaches the planet. Earth's axial tilt, the angle between its rotational axis and the plane of its orbit, varies between about 22.1 and 24.5 degrees over a cycle of about 41,000 years. Greater tilt means more extreme seasons. Less tilt means milder seasons. Currently, Earth's tilt is about 23.5 degrees and decreasing. Finally, Earth's axis wobbles like a spinning top in a cycle called precession, which takes about 26,000 years. This changes which season corresponds to the point in Earth's orbit when we're closest to the Sun. None of these cycles changes the total amount of sunlight reaching Earth by much, but they change how that sunlight is distributed across seasons and latitudes. The key insight is that cooler summers in the northern hemisphere, where most land is located, allow winter snow to persist through summer. This snow reflects more sunlight, cooling the region further, allowing more snow to accumulate the next winter. Over thousands of years, this positive feedback builds ice sheets kilometers thick. Ice core records from Antarctica and Greenland, preserving layers of snow deposited over hundreds of thousands of years, confirm this pattern. They show CO2 and temperature rising and falling in sync with glacial cycles, with CO2 amplifying the temperature changes triggered by orbital variations. During the last glacial maximum, about 20,000 years ago, ice sheets up to 3 kilometers thick covered Canada, Northern Europe, and parts of Asia. Sea level was about 120 meters lower than today because so much water was locked up in ice. Britain was connected to continental Europe. Indonesia was part of mainland Asia. Humans and animals could walk from Siberia to Alaska across the Bering Land Bridge. The climate was not just colder, but drier. With less water vapor in the atmosphere, deserts expanded. Much of the Amazon rainforest was replaced by grassland. Coral reefs nearly disappeared. Then, starting about 19,000 years ago, Earth began to warm. Orbital changes increased summer sunlight in the northern hemisphere. Ice sheets began melting. As they retreated, they uncovered darker land and ocean, which absorbed more sunlight, accelerating the warming. The release of CO2 from the ocean as it warmed amplified the effect further. By about 11,700 years ago, the Ice Age had ended, and the Holocene epoch began. The warm, stable period in which human civilization developed. But ended isn't quite right. We're in an interglacial period within an ice age. Ice sheets still cover Antarctica and Greenland. If orbital cycles continue as they have, another glacial period should begin in about 50,000 years, though human-induced climate change may delay or prevent this. Fire, too, has shaped Earth. Not just literal fire, but volcanic eruptions, supervolcano explosions, and periods of intense volcanic activity, called large igneous province eruptions. The Deccan traps in India, the Siberian traps in Russia. These are the remnants of massive volcanic events that released enormous quantities of lava, ash, and gas over periods ranging from tens of thousands to millions of years. The Siberian traps eruption, about 252 million years ago, coincided with the Permian Triassic extinction, the largest mass extinction in Earth's history. Over 90% of marine species and 70% of terrestrial species disappeared. The volcanic eruptions likely released massive amounts of CO2, methane, and sulfur compounds, causing rapid warming, ocean acidification, and oxygen depletion. Supervolcanoes, though less frequent, can have catastrophic short-term effects. The Toba eruption in Indonesia, about 74,000 years ago, ejected roughly 2,800 cubic kilometers of material into the atmosphere. The resulting volcanic winter may have cooled global temperatures for years, though exactly how severe the effects were remains a topic of ongoing research. Some genetic evidence suggests human populations may have been reduced to as few as a few thousand individuals, though this bottleneck hypothesis is debated. Volcanic eruptions also have cooling effects. Sulfur compounds released during eruptions form aerosols in the stratosphere, reflecting sunlight and temporarily lowering global temperatures. The 1991 eruption of Mount Pinatubo in the Philippines cooled global temperatures by about 0.5 degrees Celsius for several years. But Earth's climate history holds an even more extreme event. About 700 million years ago, during a time called the Cryogenian period, geological evidence suggests something almost unimaginable happened. Glacial deposits, the unmistakable signatures of ancient ice, have been found in rocks that were located near the equator when they formed, not at the poles, at the equator. This led scientists to propose what's called the Snowball Earth hypothesis. Based on the widespread distribution of glacial deposits, magnetic signatures showing they formed at tropical latitudes, and unusual rock formations that suggest a planet-wide freeze, many researchers think Earth may have experienced extreme glaciation events where ice covered the planet from pole to equator, or nearly so. Here's the puzzle that makes this hypothesis so compelling. If you get enough ice covering Earth, it reflects sunlight back into space. The planet cools further, more ice forms, more sunlight is reflected. It's a runaway feedback loop that, according to climate models, could freeze the entire planet solid in a geologically short time, perhaps just a few thousand years. The evidence for widespread cryogenian glaciation is strong. There were at least two major events: the Sturcian glaciation, lasting from about 720 to 660 million years ago, and the Marinoan glaciation, ending around 635 million years ago. Glacial deposits from these periods appear on every continent, in locations that paleomagnetic data shows were at low latitudes, places where glaciers shouldn't form unless the entire planet is cold enough. Perhaps most telling are banded iron formations that reappear during this time. These rocks form only when oceans become depleted of oxygen, which would happen if the ocean surface was sealed beneath thick ice, cut off from the oxygenated atmosphere. For hundreds of millions of years, banded iron formations had been absent from the geological record because the ocean had become oxygenated after the Great Oxidation Event. Their reappearance during the Cryogenian suggests the ocean was again becoming anoxic, sealed off from the atmosphere. But here's where it gets interesting. Not all scientists agree on how complete the freeze was. Some researchers support the full, hard snowball scenario, where ice covered the oceans entirely, reaching thicknesses of perhaps a kilometer or more. Others favor a slushball Earth model, where ice covered much of the planet, but thin ice or patches of open water persisted near the equator, allowing some photosynthesis to continue. Computer models run by climate scientists have shown that even with global temperatures well below freezing, patches of open water could persist in tropical regions under certain conditions. If there's enough heat transport from the equator, if ice is thin enough to be partially transparent, or if volcanic dust darkens the ice surface, reducing its reflectivity. And the fossil record, while sparse during this time, doesn't show the complete extinction we might expect from a total freeze. Some organisms, particularly simple multicellular eukaryotes, appear to have survived the glaciations, suggesting refugia existed somewhere. So which was it? We don't know with certainty. The debate continues. But either way, the Cryogenian was a time of extreme cold, unlike anything Earth has experienced since, when ice reached places it never reaches today, and life was pushed to the very edge of extinction. How could Earth recover from such a state? Here's where the planet's own geology provides an answer. Volcanoes never stopped erupting. Even with ice covering the surface, volcanic activity continued beneath and occasionally punched through, releasing carbon dioxide into the atmosphere. Normally, weathering of exposed rocks would consume this CO2. Removing it from the air through chemical reactions with silicate minerals. But with land covered in ice and little exposed rock or liquid water available, weathering slowed to nearly zero. CO2 accumulated. For millions of years, it built up in the atmosphere until the greenhouse effect became powerful enough to melt the ice. When the melting began, it would have accelerated rapidly, the same feedback loop running in reverse. Less ice meant less sunlight reflected, more warming, more melting. The aftermath must have been dramatic. With CO2 levels potentially hundreds of times higher than today, temperatures would have soared. The planet swung from icehouse to hothouse in geologically rapid time. Enormous amounts of carbonate rock, called cap carbonates, formed as the excess CO2 dissolved in seawater and combined with calcium and magnesium, leaving distinctive layers found worldwide atop glacial deposits. Physical evidence of this dramatic climate whiplash. What makes the Snowball Earth episodes even more intriguing is their timing. The first event, around 720 million years ago, was followed by increasing complexity in life forms. The second, ending around 635 million years ago, was followed several tens of millions of years later by the Ediacaran fauna, Earth's first large, complex organisms, and eventually the Cambrian explosion, when most major animal groups appeared in the fossil record. Could these extreme climate events have somehow spurred evolutionary innovation? The stress of near-total extinction, followed by dramatically changing conditions during recovery, may have created opportunities for new survival strategies and body plans. It's one of geology's great ironies. The most catastrophic climate events in Earth's history may have paved the way for complex life, including us. Secrets in stone rocks are Earth's memory. They record the planet's history in layers, minerals, and fossils, a chronicle written over billions of years. There are three basic types of rocks, classified by how they form. Igneous rocks form when magma or lava cools and solidifies. If magma cools slowly underground, it forms intrusive igneous rocks with large crystals, like granite. If lava cools quickly at the surface, it forms extrusive igneous rocks with small crystals or glass, like basalt. Sedimentary rocks form from accumulated sediments, particles of rock, minerals, or organic material that settle in layers. Over time, burial and compaction cement these sediments into rock. Sandstone forms from sand, shale from mud, limestone from shells, and carbonate precipitates. Sedimentary rocks often contain fossils, the preserved remains or traces of ancient organisms. Metamorphic rocks form when existing rocks are subjected to heat and pressure intense enough to change their mineral structure without melting them completely. Limestone can be metamorphosed into marble. Shale can become slate, then schist, then gneiss, as temperature and pressure increase. These rock types cycle through each other over geological time in the rock cycle. Igneous rocks weather into sediments, which lithify into sedimentary rocks, which may be buried and metamorphosed, which may melt and return to magma, beginning the cycle again. The entire process can take hundreds of millions of years. But rocks don't just tell us what they are. They tell us when and where they formed and what conditions existed at the time. Radiometric dating uses the decay of radioactive isotopes to determine a rock's age. For example, uranium-238 decays to lead-206 with a half-life of 4.47 billion years. By measuring the ratio of uranium to lead in a mineral and knowing the decay rate, we can calculate when the mineral crystallized. Different isotopes are useful for different age ranges. Carbon-14, with a half-life of only 5,730 years, is useful for dating organic materials up to about 50,000 years old. Potassium-40, with a half-life of 1.25 billion years, can date rocks billions of years old. The oldest known rocks on Earth's surface, from the Acosta gneiss in Canada, are about 4.3 billion years old. The oldest minerals found, zircon crystals from Western Australia, are even older, up to 4.4 billion years. These tiny crystals, each smaller than a grain of sand, survived the destruction and recycling of the rocks they originally formed in, providing a glimpse of the Hadean Eon, Earth's earliest and most violent period. Chemical and isotopic analysis of these ancient zircons suggests they crystallized from magma that had interacted with liquid water. This implies oceans existed at least 4.3 billion years ago, surprisingly early in Earth's history. Fossils, the preserved remains or traces of ancient organisms, provide another way to read Earth's history. Most fossils form when organisms are buried in sediment that hardens into rock. Hard parts, shells, bones, teeth, preserve more easily than soft tissue, though under exceptional conditions, even soft tissues can fossilize. The fossil record documents the history of life on Earth, showing how organisms evolved, diversified, and sometimes went extinct. Early fossils are rare and mostly microscopic. The earliest widely accepted fossils are stromatolites from 3.5 billion years ago. Fossils of complex multicellular organisms don't appear until about 600 million years ago, in the Ediacaran period. The Cambrian explosion, about 541 million years ago, marks a dramatic increase in fossil diversity. Within a geologically short period, maybe 20 million years, most major animal groups appeared, including ancestors of arthropods, mollusks, echinoderms, and chordates. Why life diversified so rapidly after billions of years of slow change remains debated, but rising oxygen levels, evolution of predation, and the Snowball Earth glaciations may all have played roles. Fossils also allow us to correlate rocks from different locations. Certain species existed for relatively brief periods geologically, then went extinct. Finding fossils of these index fossils in rock layers allows geologists to determine that those layers formed during the same time period, even if the rocks are on different continents. Paleomagnetic data recorded in rocks provides another powerful tool. As igneous rocks cool, magnetic minerals align with Earth's magnetic field. As sediments settle, magnetic grains also align with the field. These frozen magnetic directions reveal the latitude where the rock formed and, by comparing with known magnetic reversals, can help determine age. Paleomagnetic studies have confirmed plate tectonics by showing that continents have moved over geological time. They've also helped reconstruct past positions of continents by showing that rocks, now at mid-latitudes, formed near the equator or poles. Climate information is also preserved in rocks. Glacial deposits, distinctive rocks formed by ice, mark past ice ages. Their distribution shows how far ice sheets extended. Evaporite deposits, salts left behind when seawater evaporates, indicate hot, dry climates. Coal deposits, formed from ancient swamp vegetation, show where tropical or subtropical conditions persisted long enough for thick plant material to accumulate. Oxygen isotopes in shells and ice cores provide temperature records. Water molecules containing heavier oxygen-18 evaporate more slowly and condense more readily than those with lighter oxygen-16. The ratio of these isotopes in shells, which incorporate oxygen from surrounding water, varies with temperature. By analyzing oxygen isotope ratios in marine fossils from different depths in sediment cores, scientists can reconstruct past ocean temperatures. Ice cores from Antarctica and Greenland preserve an even more direct climate record. Each year's snowfall creates a layer, and by counting layers, scientists can date the ice. Bubbles trapped in the ice preserve ancient atmosphere, allowing direct measurement of past CO2 and methane concentrations. The longest ice cores extend back about 800,000 years in Antarctica, covering multiple glacial cycles. Chemical weathering patterns preserved in ancient soils, called paleosols, provide additional climate information. Soils that formed in tropical climates have different mineral compositions than those from temperate or polar regions. From all these sources, radiometric dates, fossils, paleomagnetic data, isotope ratios, sedimentary structures, geologists have pieced together a remarkably detailed history of Earth. We know when the first continents formed, when life began, when the atmosphere became oxygenated, when Snowball Earth events occurred, when complex life appeared, when mass extinctions happened, and when the continents were assembled and fragmented. Every outcrop, every rock sample, every fossil adds another piece to the puzzle. The story is still being written, still being refined, but the broad outlines are clear. Earth has changed constantly over its 4.54 billion year history, yet the same fundamental processes, plate tectonics, erosion and sedimentation, the rock cycle, evolution, have operated throughout, writing the planet's autobiography in stone. The sixth extinction. Earth has experienced 5 mass extinctions in the past 500 million years, events so severe that more than 75% of all species disappeared within a geologically short period. But here's something that might surprise you. Each time, life came back stronger, more diverse, and more complex than before. The first, the Ordovician-Silurian extinction about 445 million years ago, was likely caused by rapid glaciation and sea level changes. As glaciers formed, sea level dropped, draining shallow seas where most marine life lived. Then, as the glaciation ended, sea level rose again, flooding the continents but bringing anoxic deep water onto the shelves, suffocating marine organisms. 2 pulses of extinction, separated by hundreds of thousands of years, killed about 85% of marine species. The second, the late Devonian extinction, about 375 to 359 million years ago, occurred in multiple pulses over several million years. Possible causes include asteroid impacts, volcanic activity, and widespread anoxia in the oceans. Coral reefs were devastated and took millions of years to recover. About 75% of species went extinct. The third, the Permian-Triassic extinction, about 252 million years ago, was the most devastating. Over 90% of marine species and 70% of terrestrial vertebrate species vanished. The cause was likely the Siberian Traps eruptions, which released massive amounts of greenhouse gases over perhaps 1 million years, causing rapid warming, ocean acidification, and widespread anoxia. The extinction was so severe that ecological recovery took 10 million years. The fourth, the Triassic-Jurassic extinction, about 201 million years ago, cleared the way for dinosaurs to dominate terrestrial ecosystems. About 75% of species went extinct. Volcanic eruptions associated with the breakup of Pangaea, releasing CO2 and sulfur dioxide, may have triggered rapid climate change. The fifth, the Cretaceous-Paleogene extinction, 66 million years ago, is the most famous. An asteroid about 10 kilometers in diameter struck what is now the Yucatan Peninsula in Mexico, creating the Chicxulub crater. The impact released energy equivalent to billions of nuclear bombs, triggering wildfires across continents, generating tsunamis hundreds of meters high, and ejecting so much debris into the atmosphere that sunlight was blocked for months or years. The resulting impact winter and collapse of photosynthesis killed about 75% of all species, including all non-avian dinosaurs. But here's the twist that should concern us. We are now in the 6th extinction, the Holocene or Anthropocene extinction. And this one is different. It's not caused by asteroids or volcanoes or ice ages. It's caused by us. Current extinction rates are estimated to be 100 to 1,000 times higher than the background extinction rate, the normal pace at which species go extinct outside of mass extinction events. Some estimates suggest we're losing species at rates comparable to past mass extinctions, though the full scope is difficult to assess because we haven't yet cataloged most species on Earth. The causes are well documented: habitat destruction, particularly deforestation and wetland drainage, overhunting and overfishing, introduction of invasive species, pollution, and increasingly, climate change. Unlike past mass extinctions, driven by single catastrophes or volcanic events, this one is driven by countless incremental decisions. Clearing a forest here, polluting a river there, burning fossil fuels everywhere. Large animals, megafauna, are particularly vulnerable. Humans have already driven many large mammal species to extinction, from woolly mammoths and saber-toothed cats to giant ground sloths and Irish elk. Island species, which often evolved in isolation without predators or competitors, have been especially hard hit. But species are also evolving and adapting. Life is remarkably resilient. The question isn't whether life will survive. It will. Life has survived far worse. The question is, what kind of world are we creating, and what will be lost before we change course? The dance with the moon. The moon is not just a light in the night sky. It's Earth's partner, locked in a gravitational dance that shapes tides, stabilizes our planet's tilt, and has influenced the evolution of life. But here's something most people don't know. The moon is leaving us. Every year, it drifts about 3.8 centimeters farther from Earth. The distance seems small, but it's been happening for billions of years. The moon that hung huge in the sky when dinosaurs walked was thousands of kilometers closer than it is now. The moon formed about 4.5 billion years ago from the debris of a colossal impact between Earth and a Mars-sized object scientists call Theia. In the aftermath, Earth was molten, spinning rapidly, completing a day in just 5 hours. The newly formed moon orbited far closer, only about 15,000 to 20,000 kilometers away, compared to 384,000 kilometers today. Imagine what Earth's sky looked like then. A massive moon, 12 times larger in apparent size than what we see now, hanging overhead. It would have filled nearly a quarter of the sky. At that distance, tides were enormous. Not just ocean tides, though those would have been massive if there were oceans. But Earth tides, the deformation of the solid planet itself. The moon's gravity pulled on the molten surface, creating bulges of rock hundreds of meters high that circled the globe twice a day. These tidal bulges don't align perfectly with the moon's position because of friction. Earth's rotation carries them slightly ahead. This misalignment creates a gravitational torque. The bulges pull the moon forward in its orbit, transferring rotational energy from Earth to the moon's orbital motion. As the moon gains energy, it moves to a higher, slower orbit. As Earth loses rotational energy, its spin slows. This process, called tidal acceleration, has been continuing for billions of years. Earth's day has lengthened from about 5 hours to 24 hours. The moon has receded from perhaps 20,000 kilometers to 384,000 kilometers. And the process continues today. We can measure it. Laser ranging experiments, which bounce laser beams off reflectors placed on the moon by Apollo astronauts and Soviet rovers, show the moon is receding at precisely 3.82 centimeters per year. We can also confirm it through the geological record. Tidal rhythmites, sedimentary rocks with layers deposited by tides, preserve information about ancient day length and lunar distance. Analysis of 620 million-year-old rhythmites from South Australia suggests Earth's day was about 21.9 hours, and the year had about 400 days. Coral and mollusk fossils also provide evidence. Many organisms form daily and annual growth bands. By counting these bands in fossil corals and clams, paleontologists can estimate how many days were in a year when the organism lived. Fossil corals from 400 million years ago show about 400 days per year, confirming the day was shorter. The moon's gravitational influence creates tides not just in the ocean, but in the solid Earth and atmosphere as well. Ocean tides are the most obvious. The moon's gravity pulls water on the near side of Earth toward it, creating a bulge. On the far side, water is pulled less strongly than Earth's center, creating another bulge. As Earth rotates beneath these bulges, any given location experiences 2 high tides and 2 low tides each day. Actually, it's not quite every 24 hours. Because the moon is also orbiting Earth, it takes about 24 hours and 50 minutes for a location to return to the same position relative to the moon. That's why tides occur about 50 minutes later each day. As Earth rotates, these bulges remain roughly aligned with the moon. But friction between the ocean and the seafloor causes the bulges to lag slightly. This creates the tidal cycle we observe, with high tides occurring about every 12 hours and 25 minutes. The sun also affects tides, though its effect is weaker than the moon's. About 46% as strong, despite being vastly more massive, because it's so much farther away. When the sun and moon align during new and full moons, their gravitational pulls add together, creating spring tides, higher high tides, and lower low tides. When they're at right angles, during first and third quarter moons, their effects partially cancel, creating neap tides, less extreme tides. Tides have shaped coastal environments for billions of years. Tidal zones, areas that are alternately submerged and exposed, are harsh but productive habitats where land and sea meet. Some scientists believe tidal pools may have been important environments for the origin of life, providing concentrations of organic molecules and cycles of wetting and drying that could drive chemical reactions leading to the first self-replicating molecules. Tides also dissipate energy. The friction between tidal currents and the seafloor converts some of the moon's orbital energy into heat, about 2.5 terawatts globally. This energy loss is why the moon is gradually receding, and why Earth's rotation is slowing. Eventually, billions of years from now, Earth and moon will become tidally locked to each other, just as the moon is already tidally locked to Earth, which is why we always see the same face of the moon. Earth's rotation will slow until a day equals a month, both about 47 current days long. The moon will hang motionless in the sky, visible from only one hemisphere of Earth, while the other hemisphere never sees it. But this won't happen for tens of billions of years, far longer than the sun will remain a stable star. Long before tidal locking is complete, the sun will expand into a red giant, engulfing the inner planets, or at least rendering them uninhabitable. For now, the moon continues its slow drift away, a reminder that nothing is permanent, not even the celestial mechanics we often take for granted. Every high tide is powered by the gradual unwinding of Earth's spin. Every full moon shines from a slightly greater distance than the one before. The moon also plays a crucial role in stabilizing Earth's axial tilt. Earth's axis is tilted 23.5 degrees relative to its orbital plane, which creates the seasons. But this tilt is not fixed. It would wobble chaotically if not for the moon's gravitational influence, which damps the variations. Mars, which has 2 tiny moons with negligible stabilizing effect, experiences axial tilt variations from 0 to 60 degrees over millions of years. When Mars's tilt is low, the poles are cold and ice accumulates there. When tilt is high, the poles receive more summer sunlight, ice sublimates, and the atmosphere thickens. These dramatic changes in climate would make the evolution of complex life much more difficult. Earth's axial tilt does vary, but only between about 22.1 and 24.5 degrees over a 41,000-year cycle, part of the Milankovitch cycles that influence ice ages. This stability, provided by the moon, may have been crucial for the evolution of life, particularly complex life that requires relatively stable environmental conditions. It's a humbling thought. The moon, born from catastrophe, has quietly shaped Earth's history for over 4 billion years. It stabilizes our axis, creates tides that may have nurtured early life, lights our nights, and continues its slow recession, a process that will eventually transform Earth's day from 24 hours to something far longer, though not in any time frame that concerns us. We are, in a very real sense, a product of that ancient collision. Without the moon, Earth would be a different world. Perhaps life would have still emerged, but it would have evolved under different conditions, in a different environment. The moon is not just a satellite. It's part of what makes Earth habitable. The fragile balance. Earth is in a Goldilocks zone, a region around the sun where temperatures are just right for liquid water to exist on the surface. Too close to the sun, and water boils away, as on Venus. Too far, and it freezes solid, as on Mars. But the habitable zone is not a single narrow band. It's a range that depends on atmospheric composition, planetary mass, and geological activity. Earth has remained habitable for over 4 billion years, despite the sun gradually brightening over that time. When Earth formed, the sun was about 30% dimmer than it is today. With our current atmosphere, this would have frozen Earth solid. Yet, geological evidence, liquid water erosion features, sedimentary rocks, possible microbial fossils, shows liquid water existed. This is the faint young sun paradox. The answer, supported by climate models and geological evidence, is greenhouse gases. Earth's early atmosphere likely contained much higher levels of carbon dioxide and perhaps methane than it does today. These gases trapped heat, keeping the planet warm enough for liquid oceans despite the dimmer sun. As the sun brightened over billions of years, carbon dioxide levels decreased, regulated by the carbonate-silicate cycle. Weathering of rocks consumes CO2, and the formation of carbonate sediments locks it away in limestone and other rocks. As temperatures rise, weathering accelerates because warm temperatures increase rainfall and speed up chemical reactions, removing more CO2 and preventing runaway warming. This negative feedback stabilized Earth's climate, allowing temperatures to remain in a range suitable for life even as external conditions, the sun's luminosity, changed dramatically. But this stability is not guaranteed. Earth has come close to catastrophic climate tipping points. During Snowball Earth events, ice covered much or all of the planet, reflecting sunlight and cooling it further in a runaway positive feedback. Only volcanic CO2 accumulation over millions of years eventually reversed the freezing by building up greenhouse gases that overwhelmed the ice albedo feedback. In the opposite direction, if greenhouse gas levels rise too high, Earth could experience runaway warming. Venus may have once had oceans, similar to early Earth, but as the sun brightened, temperatures rose. Water vapor, itself a greenhouse gas, evaporated into the atmosphere, trapping more heat, evaporating more water in a runaway greenhouse effect. Eventually, all the water evaporated. Ultraviolet light split water molecules into hydrogen and oxygen. The light hydrogen escaped to space, leaving Venus with no water and a crushing CO2 atmosphere with surface temperatures hot enough to melt lead. Earth avoided this fate because it was slightly farther from the sun, giving the carbonate-silicate cycle time to remove CO2 before temperatures reached the runaway threshold. But the margin may have been narrower than we'd like to think. Earth's habitability also depends on factors beyond climate. The magnetic field protects the atmosphere from solar wind erosion. Plate tectonics recycles carbon and nutrients, preventing all carbon from being locked away in rocks, which would eventually starve life of this essential element. The moon stabilizes axial tilt, preventing extreme climate variability. Life itself helps maintain habitability. The Gaia hypothesis, proposed by scientist James Lovelock in the 1970s, suggests that life regulates Earth's environment, keeping conditions suitable for life. While controversial in its strong form, that Earth is a self-regulating superorganism, the idea that life, An environment are deeply interconnected is well supported. Photosynthetic organisms produce oxygen and influence atmospheric composition. Plants increase weathering rates by secreting organic acids that break down rocks, affecting CO2 levels. Marine organisms affect cloud formation by releasing chemicals like dimethyl sulfide that seed clouds. Bacteria in soil and ocean mediate nutrient cycles that affect how carbon, nitrogen, and other elements move through the Earth system. In countless subtle ways, life influences the physical and chemical environment, and the environment influences life. They co-evolve, each shaping the other in a complex dance that has continued for billions of years. But this balance is fragile. Human activities, burning fossil fuels, clearing forests, releasing pollutants, are altering Earth's systems faster than they have changed naturally in millions of years. Atmospheric CO2 is higher than it has been in at least 3 million years, possibly longer. Global temperatures are rising. Ice sheets are melting. Sea levels are rising. Ocean chemistry is changing as the ocean absorbs CO2 and becomes more acidic. These changes test the resilience of Earth's systems. Some changes may be reversible if we act quickly. Others may cross tipping points, triggering feedbacks that are difficult or impossible to stop on human timescales. The collapse of the West Antarctic ice sheet, once started, may be irreversible on timescales of centuries to millennia. The thawing of Arctic permafrost could release vast amounts of methane and CO2, amplifying warming in a positive feedback. The dieback of the Amazon rainforest could shift the region from a carbon sink to a carbon source, further accelerating climate change. We are conducting an uncontrolled experiment on the only planet we have. The outcome is uncertain, but one thing is clear: the Earth will endure. It has survived far worse: asteroid impacts, snowball glaciations, runaway volcanism, and 5 mass extinctions. The question is not whether Earth will survive, but whether human civilization will endure, and what kind of world we leave for future generations, and the millions of species that share this planet with us. Reflections on a blue dot. Earth is the only place in the universe we know for certain harbors life. Billions of stars exist. Countless planets orbit them. But so far, despite decades of searching, we have found life on only one small, blue, fragile world orbiting an average star in an ordinary spiral galaxy. This makes Earth precious beyond measure. We've explored its heights and depths, from the peak of Mount Everest, nearly 9 kilometers above sea level, to the Challenger Deep in the Mariana Trench, nearly 11 kilometers below. We've drilled into its crust, studied its rocks, mapped its ocean floors and atmospheric currents. We've measured its age, traced the movements of its continents, deciphered the history written in ice cores and tree rings, and layers of sediment. We've learned that Earth is not a collection of separate systems, but a single, interconnected whole. The atmosphere influences the ocean. The ocean influences the land. The land influences life. Life influences the atmosphere. Change one part, and ripples spread through the entire system. We've learned that Earth is old, unimaginably old by human standards, but young in cosmic terms. It has existed for a third of the age of the universe. It will exist for billions of years more, though the sun's evolution will eventually render it uninhabitable. Perhaps in 1 billion years, certainly within 5 billion when the sun expands into a red giant. We've learned that Earth is dynamic. Continents drift. Mountains rise and erode. Oceans open and close. Ice advances and retreats. Life evolves, adapts, and sometimes goes extinct. Nothing is permanent. Everything is in motion. We've learned that we are part of Earth, not separate from it. The atoms in our bodies were forged in stars. The water we drink cycled through ancient seas. The oxygen we breathe was produced by cyanobacteria billions of years ago. We are stardust, given form and consciousness on a planet that, through a series of unlikely circumstances, became habitable, and remains so. But here's the final truth, the one that should change how you see everything. Earth didn't have to be this way. Think about everything you've heard tonight. The moon-forming impact could have destroyed the planet entirely, or knocked it into an orbit too close or too far from the sun. The magnetic field could have failed, as it did on Mars, allowing the solar wind to strip away the atmosphere. The Snowball Earth events could have frozen the planet permanently, with no volcanic CO2 to eventually thaw it. The Great Oxidation Event could have poisoned all life, instead of opening new evolutionary possibilities. Any of the 5 mass extinctions could have been total, leaving Earth as a planet of bacteria, with no complex life ever evolving. At dozens of points in Earth's history, everything could have gone wrong. One different variable, one slightly different condition, and we wouldn't be here. But it didn't go wrong. The planet froze, and it thawed. It was struck by asteroids, and life recovered. It lost most of its atmosphere, multiple times, and rebuilt it. The magnetic field fluctuated and reversed, but never disappeared. 5 times, extinction nearly claimed everything, and 5 times, life found a way back. Earth is not just a planet. It's a 4.5 billion year old survivor. A world that has been through hell and emerged over and over as a place where life can thrive. Tonight, you've heard 100 facts about Earth. But facts are just the beginning. They're doorways to deeper understanding, connections between phenomena, stories written in rock, ice, and the fossil record. Every mountain range is a collision frozen in stone. Every glacier is a climate archive. Every fossil is a message from the deep past. The very air you breathe is a gift from organisms that died billions of years ago. As you drift off tonight, remember that you're on a journey through space, orbiting a star at 107,000 kilometers per hour, spinning on an axis at over 1,600 kilometers per hour at the equator. You're part of a solar system racing through the Milky Way at 828,000 kilometers per hour. You're part of a galaxy moving through the universe. But you're also here, on Earth, nestled in its thin atmosphere, held gently by its gravity, warmed by its sun, protected by its magnetic field, and connected to billions of years of history written in every rock, every drop of water, every breath of air. You're standing on a planet that shouldn't exist, breathing air that was once poison, protected by forces you cannot see, and carrying within you atoms forged in the hearts of stars. Sleep well, and thank you for exploring our impossible, improbable, beautiful home with me tonight. If you enjoyed this quiet journey through Earth's story, consider subscribing to Sleepable Science. There are more worlds to discover, more mysteries to unfold, and more gentle voyages through the cosmos waiting for you.